Alright, so in this video we discussed the third part of differential equations, which is applications. We're going to go over just two applications out of the many possible applications. One of them that we're going to cover unlimited growth, and the other that we cover is limited growth. Okay, so what about these situations? Well, let's look at a very, I would say, kind of fictional situation, but this is going to help us get a feel of how exponential functions are heavily related to differential equations and situations like this. For example, we have for unlimited growth, this is the differential equation that gives rise to the solution, which is given right here. Okay, so what about it? So we have some quantity. By the way, here I should have wrote Q. Quantity Q grows at some rate. Call it y prime, but this y prime is really dq over dt, and it's proportional to the present size. Okay, this also has to be a Q and a Q. Okay, so the trick is, well, so the change of the quantity with respect to time is proportional to its present quantity. Okay, however, to change this proportionality symbol into an equal sign, we need to introduce constant of proportionality. Okay, so this will give us the dq over dt, that differential equation. The details on how to get from here to there, well, that basically requires separation of variables. I'll let you read the textbook for that derivation. Let's just go ahead and do an example. Okay, so under ideal conditions, the rate of growth of bacteria in a culture is proportional to the size of the culture at any time t. So suppose that initially we have 10,000 bacteria in the culture, and after 2 hours we record that we have 60,000 bacteria. Okay, so how many bacteria will there be in the culture at the end of 4 hours? So first of all, let's write our givens. This is 10,000 bacteria initially. Okay, so that means that Q initial or Q naught equals 10,000. And this sentence right here will be very useful. 60,000 are present 2 hours later. This is giving us an initial condition for the equation. This is telling us this is telling, okay, that sentence I highlighted in green means that Q of 2 equals 60,000. Okay, now let's write down the formula and plug in all we know. Okay, so Q at any time t equals Q initial e to the kt. So in this case, we know the initial. We can just plug it in, the initial amount of bacteria, which is 10,000 e to the kt. But what do we have here? We have essentially one equation with two unknowns. We don't know the time, we don't know the k. So we need to find k. How are we going to find k? Well, this sentence that we highlight in green, the initial condition, will be helpful to find k. Okay, what does that mean? What does the with Q of 2 equals 60,000? This means that when t equals 2, Q equals 60,000. Okay, now plug it in, plugging in q of 2 equals 10,000 e to the k times, so when t equals 2, okay, so on the right hand side of the equation we get 10,000 e to the 2k. And what is q of 2? From the condition, q of 2 is the same as 60,000, the one I'm highlighting here. To replace this with a 60,000. Okay, so let's divide both sides by 1,000 to get to solve for k. So we are going to get e to the 2k equals 6. Now, in order to get rid of that exponential, do ln on both sides. And 2k equals ln of 6, giving us at the end k equals 1/2. Oops, I used the wrong color here. 2k equals 1/2 ln of 6, k equals 1/2 ln of 6. And we're going to use a calculator here. Okay, we use a calculator and let this be 0.896. Okay, so that's k. What do we have now? We go sorry about that. We go from the given equation that we had without k. We go and rewrite it with the corresponding value of k, the one that we just found. So q of t equals 10,000 e to the 0.896 t. Okay, so now they're asking us to answer the following question: how many bacteria will there be in the culture at the end of 4 hours? Okay, so now we can use this function right here to find whatever value of q, that is the number of bacteria at any time, 5 hours, 7 hours, 1,000 hours, etc. In this case, they're asking us to evaluate this for 4. So just plug it in, e to the 0.896 times plug in 4, and in this case use a calculator to get the following answer. We get 360 times and 173 bacteria. Okay, that's the final answer. That's how we deal with a problem dealing with unlimited growth. All right, so well, again, earlier in this video I mentioned this is a sort of fictional situation because growth is never unlimited. Growth is actually limited to, number one, limitations of space, limitations of food, or limitations on our capacity to memorize things. So that's going to be very important. That's another of the applications of the other type. Okay, so all right, so for example, that's what I was mentioning earlier. Restrictions of food and space would eventually slow down this growth. Okay, let's look at the profile right here real quick. So, for example, this looks like an exponential function. Notice how this growth goes on forever. However, that's not real. What is more real here is the growth goes more like this. Starts growing fast and then suddenly goes with like an asymptote here. It goes due to the size, some quantity c, or rather I would call it q c, which is q max rather. Okay, So which is, for example, the size of a population, the size of the population size of a city. For example, like in the example that we're going to go over here, which is a town that has 50,000 people. Okay, so we're going to deal with a situation in which we have the disease spread in a town with 50,000 people, in which we know that after 2 hours, 30,000 people have been infected with the disease. Number one, we need to find a formula for the number of people that have been infected within 2 weeks. That is 1 week, 2 weeks, etc., any number of weeks, and then find out how many people have been in or will be infected within 6 weeks. Okay, just briefly, let me explain the formula. So this is very similar to um, this the other type of growth, the limited growth. However, in this case, this is the maximum capacity, and then the amount of people, for example, that gets infected every time. Because, for example, if for example the town that we are working with, it's comprised by 50,000 people, there's no way to have more people than it already is, right? So that wouldn't make sense. And then the model, if you read the book, this is the model they show us here. However, I will use a very simpler model in terms of simply the initial amount of the population. Okay, so let's see. So what do we have here? So we have some Q initial. We have some Q initial of 50,000 people. Okay, then this sentence right here, after 2 hours, not 2 hours, actually this should be weeks. Okay, after 2 weeks, 30,000 people have been infected. So that means Q of 2 equals 30,000. Okay, so this is going to be our initial condition, the same way we used to find K. So let's write down the equation. So Q at any time equals Q naught minus Q naught e to the negative KT. Okay, so we know the Q naught equals, okay, let me factor it out to make it even more simple. This is 1 minus e to the negative kt. That way we don't have to write that big number twice and simplify our calculation. So this qt will be equal to 50,000 times 1 minus e to the negative kt. So we need to find k first. Okay, we need to find k, and we can use the initial condition that is highlighted here. Q of 2 equals 30,000, which means that when t equals 2 weeks, the amount of people infected, Q, equals 30,000. Okay, so let's put it in the symbols that we have. So Q of 2 equals 50,000 times 1 minus e to the negative k times 2. So essentially we're plugging into whatever we see the letter T. Okay, so this will be 30,000 equals to 50,000 times 1 minus e to the negative k, or rather 2k. Okay, so if we divide both sides by 50,000, we get we get 1 minus e to the negative 2k equals 3/5. Then let's subtract 1 to both sides. To get negative e to the negative 2k equals, so 1 minus 3/5 is, well, it's going to be a negative number. That's going to be 2/5. And then let's divide both sides by -1 to get e to the negative 2k equals 2/5. Then we take ln to both sides to get rid of this exponential, and we get negative 2k equals ln of 2/5. Finally, we divide both sides by -2 or multiply by -1/2. Notice how these 2's go away, and this will give us k equals, so let's use a calculator to evaluate this quantity. So 1/2 times ln of 2/5. Okay, so that's going to give us, times a negative, would give us 0.458. Okay, so now that we have that k value, the rate basically, let's write this q of t equals 50,000 e to the times 1 minus e to the negative 0.458 t. Okay, and now we're going to use this formula to find how many people will be infected within 6 weeks. That is, let's evaluate q of 6. 1 minus e to the negative 0.458. Plug in 6, plug in 6. So q of 6 will be, okay, let's plug all this in the graphing calculator. So all we do is 50,000 times 1 minus e to the negative 0.458 times 6. And we get 46,797 people. All right, so that's the amount of people that will get infected after 6 weeks. How do we know this makes sense? Well, what is the maximum amount of the largest number that you can get? For example, if let's say you plug in an infinity here, plug in an infinity, that whole term will go to 0 because the exponential to the negative infinity will turn that into 0. 1 minus 0 is 0. I mean, 1 minus 0 is 1, and then that times 50,000. So the maximum amount of people is 50,000. So it means that it would take infinity number of ideally it would take an infinitely many amount of weeks for the entire population to get infected. If you get a number that is larger than the amount of people in the town, maybe you did something wrong on the calculation. So I would double check maybe your ln's, or when solving the equation, or maybe plugging in the wrong plugging the number in the wrong letter. Okay, so this was briefly a couple of applications of differential equations. Again, like I mentioned, there's countless of applications to physics, electronics, chemistry, biology, well, here we have some basically biology um, applications. So this is the end of this video, right? See you next time.